I've been reading through Apple's color management overview document, and I want to share some of what I've learned with you. For those of you who aren't familiar with this, usually it's much faster than this, I'm using a tool called Tinderbox, which is great. I know it looks a little bit like a mind mapper, but it's actually a lot more than that, and I highly recommend you look at it. So to begin with, human beings have eyes, and their eyes have trichromatic color vision. Now what that means is that we perceive one color when sometimes there are two different spectral phenomena. And here's what that means. Color is represented in a spectrum of light by a single wavelength. So you'll have the red wavelength, the blue wavelength, the green wavelength. I'm just naming those as examples. Just call them wavelength A, wavelength B, and wavelength C, disconnected from any color. The eye, as it's constituted, can perceive two different spectra as one color. Okay? Now that takes a little bit of thinking to get used to, and I drew this to help you understand that. So what that means is that you can have a color from the additive colors, and it can be one set of phenomena, and you can have a color from the subtractive colors that impacts the eye, and they'll both be perceived as one blue, even though they're two completely separate phenomena. So there's not a one-to-one correspondence between the phenomena hitting the eye and the color that you perceive. And this is known as metamerism. Okay? This is all specified in the Apple document. It's actually quite interesting. Let's go back and look at the eye as a mechanism for a minute. So you have receptors, and you have rods and cones, as you learned in school. The rods pick up illumination but no color, and the cones have a chemical on them called rhodopsin. And its base color is yellow, so it starts out there, and it's sensitive to yellow, but then it's sensitive to reds and blues, so it modifies those. And if you'll notice, those are the three primary colors that we then mix together to get other things, although in the case of emitted light, we mix together red, blue, and green. So the color the eye sees, you see it at the back of the eye, the fovea, that's where most of the cones are, and you see red light, green light, and blue light back there. So most of the reaction is going to be happening back there. There are a couple of kinds of light. There's direct light and there's filtered light. Okay. Let's go through here. So, what makes this possible? Okay, let's back off for a minute. So, spectral light, light coming from the spectrum, extremely expensive to reproduce that. So, what we do instead are take additive colors, red, blue, and green, and use them to come up with the other colors. So in other words, we don't just produce something that produces the wavelength magenta, which actually is a wavelength on the rainbow spectrum. Instead, we mix red and blue and come up with something that triggers the eye the same way magenta does, and that's known as an additive color. Okay? And if we mix red and green, we get yellow. If we mix blue and green, we get cyan. If we mix red and blue, we get magenta. Okay? These are used in TVs and monitors. It's used wherever you're emitting light, right? So there's no additive, there's no color besides the ones that you're mixing together. Subtractive colors are very different. For one thing, it's used for printing. And it works off what objects that aren't emitting light but are reflecting light absorb. So for example, when you see a red apple, what you're really seeing is an object that's absorbing blue and green light so that you don't see it, and it's bouncing back red light. Okay, so they use CMYK to indicate this system as opposed to RGB, and that means cyan, magenta, yellow. If you look at cyan, magenta, yellow, those are the mixed colors. So what that tells you is that if you overlap a couple of these colors in a subtractive system, you'll be eliminating two of them. So if you overlap cyan and yellow, you'll be eliminating blue and red, and you'll get green, right? If you overlap magenta and cyan, you'll be eliminating blue, green and red, and you'll get blue. Okay, so that's how that works. Also, the K in there stands for black. It's the key color, and you can use it to increase contrast, but also because it's cheaper than the other inks, they tend to pour it in there to increase the perceived quality of the color. It happens to work out. So a subtractive system subtracts light by absorbing whatever part of the spectrum it doesn't want you to see. Okay, a little bit different. That's how printers work. Now I thought I had something on there that said the light is extremely expensive to reproduce. Maybe it's somewhere else. Yes, expensive and impractical. Precise wavelengths, spectra, spectral color reproduction, trichromatic color reproduction, very expensive to do, which is why you go with additive colors and subtractive colors instead. Now, when you go to Apple's or any computer's system of dealing with light, it's not just Apple, there are standards in place for this stuff. You can have various dimensions dealing with it. You can actually, color has, so before we get to that, color itself has three dimensions. It has hue, it has saturation, and it has value. Okay? And if you look at hue, saturation, value, you'll notice that we have the HSV, a hue, saturation, value color spaces, and we'll get to that soon. And also HLS, which is the same thing. They're shaped slightly differently in terms of the squares and cones that are used to describe a color space. But HLS stands for hue, lightness, and I forget what the S stands for. I'll have to look that up again. Oh, lightness and saturation. Hue, lightness, and saturation. It's reversing those two. So hue is the name of the color. It's actually the pure color on the spectrum. So it's blue or red or green. Okay? The saturation is the intensity of the color. And what that means, and I've had to do a little work to develop my own understanding of this, but it's easy to describe what it looks like, and then you sort of get it. If you see a really red apple, that's a really highly saturated color. It's dripping red, candy apple red, right? That kind of color. It's very rich. You know, you can almost taste it. If you see pink, that's an unsaturated red because the red in it is more diffuse, right? And a neutral gray has zero saturation, no color in it at all, right? So it's closer to true pure spectral color the more saturated it is. And I asked myself a question here that I don't know the answer to, so we don't need to hit that right now. Okay, and then the value or brightness, so how much light is actually being reflected, an actual quantity of light being reflected back from the image or being reflected or being transmitted by a monitor or so forth. So you know how when you turn your monitor bright or dark, it's transmitting more or less light. That's what value is, right? Okay. A lot of information in that Apple document. Very well written. Just one more of these little trees to get through. So now we understand hue, saturation, and brightness. Okay. Now we're going to go to Apple Color Sync, which is the framework Apple uses to record the colors. So you have a spectrum. So how do you represent that in digital form, right? To say, so that somebody who's making a program or painting something can say, I want red, and I want it to be really red. So how do you store that? And then how do you send it to a monitor or a printer so that that monitor or printer understands which color it's supposed to print, which dye it's supposed to pull in what combination from the ink cartridge, or what little red, blue, and green diodes in the pixel it's supposed to turn on or off, dependent upon the values you sent, right? So what is a color space? Well, color spaces are environments where you define the colors, and they can have 4 different dimensions. They can have 1 component, 2 components, 3 components, or 4 components. Okay? And what that means, 1 component isn't very interesting. 2 components means black and white. So you're going to have 2 bytes indicating what the range is between the black and the white components, and that's going to indicate what color the gray is, the grayscale it's going to be showing. Notice also these individual components are also called color channels. If you get 3 components, it's more interesting. That's RGB. So you're going to have RGB, and they're going to have a value from 0 to 1. Every single one of them is. So 0, say to 0.5, for example, to 1. You're going to pick a value that's going to be one of those. Okay? Or you can have 4 components, and the 4th component is the alpha channel, which indicates how transparent or opaque that image, that color is going to be. Okay? In an environment, in a color space, you can have colors represented, compared, computed, and ordered. And going through each of them, so you're representing a color, obviously. You can also compare 2 colors and get different numerical values from them based on this system. You can compute new colors by feeding it numerical values, and you can order those colors according to those components and those numerical values, depending upon how you want to sort them out. Color spaces are also represented alphabetically, and I recommend you go look at the book, but you'll see this is actually the difference between HSV and HLS. You'll see cubes and cones and polyhedra are used to represent these physically. Go take a look at that. So let's go. There are different kinds of spaces. And again, this relates back to the components we were just discussing down here. They're grayscale display and printing spaces. And if we go over here, we'll see it's 1 component, black to white. Oh, I'm sorry, so 2 components is something else. 1 component, black to white. I'm still working on my own understanding of this. So now I don't know what 2 components are. I'll have to go back and look that up. RGB color spaces for displays and something else mysterious here. Displays and scanners, there we go. Including HSV and HLS. And we note that there's also an sRGB color profile. So we'll get into what a color profile is in a minute. But essentially it's a means of translating these color component definitions into the actual analog or digital signals that are sent to the devices in order to get the right red on them. Okay? And we know they have a gamma of 2.2 and a white point in Kelvin of 6,500 degrees, right? CMYK color used for printing. Then we have device-independent color spaces, and what that means is that here and here, these are probably device-dependent most of the time, depending, these are specific to the Mac, for example, or a Windows, say a Lenovo or an IBM laptop, or this would be a CMYK color. Not necessarily Apple ColorSync, of course, if they would use their own system, but it would be specific to a specific kind of monitor. Named color spaces are used in printing and graphic design. Then they have a new concept called a hi-fi color space. This is the latest thing, and it can handle red-orange printing and gold and silver metallic. And I forget, red-orange printing has a special significance because and I'm pulling this from memory, but because most monitors represent red very badly, as I recall, and so they approximate a red-orange. Monitors and RGB in general represent certain colors very well and certain colors very poorly. It can only approximate them, and red is not one of the things it does very well. And this is supposed to correct some of that, I believe. I don't know what LAB is. I was going to look it up before I did this presentation. I didn't do it. And I believe that's what I have to show you right now. I'll come up with more of this at some other point. Let's see, how far down did I shrink this? Yes, that's all there is right now. Again, I highly recommend you look at Tinderbox. It's pretty great. And I'll come back and do some more on this at some point. If you'd like a copy of this Tinderbox document, feel free to reach out to me.